Hello, this is a list of new nodes that we are going to discover along this lesson. We will not just study these nodes, but take in practice each of them for its intended purpose. At the end we will extract the transformation matrix from the animated object. Okay, let's get started. This time I'll use a pig head. Let's dive inside. Remove this checkbox just to get rid of the shader. Put a 10 to uniform scale. I want to make the background black. Press D in the viewport, then go to the background menu and select dark. That's it, now let's drop down the attribute VOP. Connect the pig head, then dive inside. Now I want to show you the align node. Let's create it. This operator computes a matrix representing the rotation. To align the geometry in the specified direction, we just need to multiply the position vector by the output matrix of this node. Before multiplying, I want to adjust the initial settings of the align node. Since the pig's face is directed along the positive z-axis, we will set the same direction for the first vector. The second vector is directed along the positive y. Now let's multiply the position by the output matrix. Look, we aligned the pig head along the positive y. Of course we can align any direction we like by changing this vector. Okay, let's move on. Now I want to align the pig head using some primitive. Let's create a sphere. We also need a transform node. Then connect the sphere to the second input. Let's move the sphere in front of the pig's nose. Something like this. Okay, now I'm going to import the sphere position. Connect the second geometry to it. Create a constant to specify a point number of 0. Now we can use the sphere's position as an alignment vector. Okay, let's jump at the object level, then tweak the sphere and see what we get. Here we go, the pig's head is always looking at the sphere. Let's move on. The align node is able to output a quaternion. Let's duplicate the align node. Then choose an angle axis from this menu. That's it, now the output is a quaternion. Let's check if the result will be the same. For that we need a rotate by quaternion node. Connect position to it. Then quaternion. The output vector goes to the P. Let's check out. As you can see, the result is absolutely the same. Okay, now we can remove the nodes associated with the quaternion. Then return the old connection. Okay, now I want to show you the problem that you will face when using this node in most cases. Look, now I'm pulling the sphere inside the XZ plane. As you can see, the pig's head follows the sphere without any flipping. Now let's move up a bit the sphere, then try again. Take a look, the pig's head is flipping. Okay, now I want to show you another node that you can use to avoid flipping, and in addition it gives us some extra control. The node is called look at. This operator computes a 3x3 rotation matrix to orient the z-axis along the vector, to from, under the transformation. If an up vector is specified, it will determine the roll. Now let's connect the sphere position to the first input. The output will replace the old connection. Great, now let's check what we have. As you can see, unlike the align node, there is no flip because the look at node has an up vector. Now let's create an extra sphere to control the up vector as well. Let's move it up. Then connect the third input. Let's duplicate the import point attribute node. Connect the third geometry to it. Okay, the second sphere is going to drive the up vector. That's it, let's check what we get. First, let's change the orientation of the pig's head. Now let's tweak the up vector. As you can see, the up vector gives us an additional control to rotate around the look at vector, and there is no flip. Okay, let's reset all tweaks, then go ahead. The look at node does not output quaternion like an align node, but if you want, this can be done through conversion by matrix 3 to quaternion. This operator converts a matrix 3, representing a rotation, to a quaternion representing the same rotation. Let's connect the rotation matrix to it, then create a rotate by quaternion node. Connect the position to it. Then connect the quaternion. The output to the P. Now let's check if the result is the same. As you can see, we have absolutely the same result. You can even do the opposite conversion from quaternion to rotation matrix. Okay, let's move on. For further work, we only need an align node, so let's get rid of the rest. Okay, now I'm going to manipulate each primitive of pig head geometry. Let's jump at the object level. We can also delete the second sphere, we no longer need it. Okay, now let's create a facet node. Turn on the unique points option, just to separate the primitives from each other. Okay, let's move on. Now let's create an import primitive attribute. This operator can fetch the primitive attribute from the specified geometry. Look, with this node I'm going to import the centroid position of each primitive. Connect to it the pig head geometry. Then we must give primitive numbers. Okay, now let's subtract the centroid position from the point position to send them all back to the origin. Here we go, they all are in the origin. Okay, now we need to do exactly the opposite, return them to their original position. Excellent, now we are able to manipulate each primitive around its centroid. Let's arrange the nodes so that there is no mess. Okay, now let's check what we have right now. As you can see, the sphere position is an alignment vector for all primitives. Let's reset the sphere tweaks and go on. Now I want to make each primitive look towards the sphere. For that we just need to subtract from the sphere position the primitive centroid positions. Okay, let's connect the difference vector to the align node. Let's check what it looks like. Here we go, each primitive looks towards the sphere. The only thing I want to change is to exclude the movement of primitives far from the sphere. Okay, let's create a distance node. We can maximize the network window. Now let's measure the distance between the sphere and each primitive. Visualize the distance attribute. Let's move the sphere closer to the pig head. Okay, now we can adjust the distance attribute. Let's fit the distance. Put a 10 for source max and 2 for source min. Okay, now let's create a mix node. Connect the alignment vector to it. Mixing will occur with a vector directed along Z. Connect to align node the mix output. Okay, let's slide the bias parameter and see what we have. Look, when bias is 1, the orientation of primitives is unchanged. And when bias is 0, each primitive looks towards the sphere. Now let's drive the bias by distance. That's it, as you noticed, the primitives that are farther from the sphere were left intact. Okay, now let's tweak the sphere and see how it looks in action. Excellent, let's move on. Delete the visualize node. Now I want to create a color based on the distance. Connect the distance to it. Instead of using this geometry VOP output, I suggest creating a new one. Connect the ramp to CD. Okay, now let's set up the color ramp. That's it, now let's tweak the sphere and see how it looks with colors. Here we go, we've created a cool effect using a few simple nodes. That's the beauty of the VOP network. Since our setup is completely procedural, we can replace the pig's head with any other geometry. Now let's replace the pig's head with a torus and make sure that everything works correctly. Put a 10 for uniform scale. Let's increase the rows and columns. Then replace the pig's head. Great, now let's check if it works as it should. As you can see, all works correctly. Now I propose to stop there and then do something new. Okay, let's get started. This time I want to show you how you can extract a transformation matrix from a moving object. Look, I've prepared this simple animation in advance, from which we're going to extract the transformation matrix and then use it to move another object. Excellent, let's create an attribute VOP. Connect the geometry to it, then dive inside.